So I'm Bryce Adelstein Lelbach, and this is a talk about AI-assisted software engineering. So my primary area of expertise is parallel programming, programming languages, and compilers. I've served in leadership roles on a number of standards bodies, including the C++ committee. I work at NVIDIA. We make parallel processors, mighty fine ones, I think. And I'm a principal architect there where I drive our strategy for HPC programming models, C++ compilers, and C++ libraries. Can we take down the lights over there a little bit? There we go, that's a little better. I use black around slides, so we're gonna need that. All right, so yeah, as I said, these two hooligans kept me up a little bit. One of them is now here, which is good, because he will be featured at some points in this talk. Connor, I think you're going to need to sit up in front.
Sean kept me up.
Yeah, we covered that. We covered that. All right, you see, we covered that. So I am not an AI expert, and I have neither the knowledge or the desire to explain how neural networks like GPT work. I want to focus today on the applied science of AI, how we can use AI technologies to transform how we develop software. It's funny, I increasingly find myself at the start of talks giving some disclaimer, which is essentially, I don't know what I'm talking about, but listen to me anyways. But I do find that one of the best ways for me to learn something is to go and give a talk about it. All right, so large language models, like the ones used in ChatGPT, are neural networks with billions or trillions of parameters that are trained on massive quantities of unlabeled text. So we interact with these models by sending them some sort of textual context in natural language. And this usually begins with, one initial question or starting prompt. And then the model will generate a response which will be added to that context. And then the interaction can be continued by adding more textual input to that context. Then the model will evaluate everything that's in the context and it will generate a new response. However, the size of the context is finite. As we add more input, older input and responses may be dropped from the context. So large input sizes may be rejected altogether. Context size is one of the major limiting factors of large language models today. And this limit especially impacts the application of AI to software engineering, as we'd like the neural network to have access to our code. So neural networks themselves are not the end game of AI. They are just building blocks. Simple AI systems may be built on top of a simple interaction with a single neural network. But there is much greater potential in complex AI systems, which are composed of webs of neural network agents and other actors such as information retrieval mechanisms and execution environments, like a web browser or a calculator because they're pretty bad at math, or a Python interpreter because they're also not so great at code. But also just the idea that maybe you have one model that does one particular type of thing and another model that does another particular type of thing, or even just different instances of the same model that have been instructed to do a different task. All right, so there are going to be a couple different interactive parts of this talk where I'm going to ask you all for input. We're not going to do the microphones for that part. I'll just repeat what you say. We'll use the microphones at the end when we get to questions. And this is the first of those parts. So what do we do? What does our work as software engineers consist of? What sort of tasks do we do? So feel free to shout out. Translate requirements. Bring ideas to reality. Search Stack Overflow. Debugging. Was that? Wait for the compiler. All right, all good answers. So I think that our work breaks down into two kinds of tasks. And they're not mutually exclusive. Some tasks sort of fall into both of these categories. So the first is creation. We create things. We create code. We create interfaces, libraries, applications, systems, documentation. We also hopefully create designs for these things before we actually start implementing them. We plan and architect. And we analyze. We analyze code. We analyze results from code. We analyze diagnostics from code, from compilers. We debug. We review code. And I believe that this second type of task is where language models shine today. They are great at taking a bunch of data and extracting information from it, especially if there's just like a right and wrong answer. If it's a closed question where there's like, hey, what's in this data set? It's much harder for them to answer an open question where you're asking them to do some sort of creative task. So let's look at an example of an analysis task. All right, so imagine that our CI fails on our PR with this diagnostic. What do we have to do to understand and fix this problem? Like if somebody submitted a bug report with solely this diagnostic, what would we tell them? Okay, we're reproducer. What would we need? A larger font? Source code? I mean, that is intentional. You're not really supposed to read this. What we need is we need more information. Like we do not have sufficient context. This is what I find myself constantly saying to bug reports to my open source projects is like, you need to provide me with more information. Here's the things that I need to know. Like show me the source code. You know, show me what version of compilers are you using. What tools are you using? Like I need more contextual information. So then how do we identify what information we would need from a diagnostic like this? Well, first we have to do some classification. What sort of tools are involved? What programming languages, data formats, etc. are involved? Also, we need to identify what code we may need to look at. What files or resources do we need to access? What source locations, code entities, or content do we need to see to help us understand this problem? Often when I get a compiler diagnostic like this, I'll go and look at it, and I'll look at the first couple source locations, and then I'll go open that up in my IDE and look at that code. And maybe looking at that code will tell me that I need to look at some other code. I think this is a process that most of us are probably familiar with to some degree. So what we want is we want to have the AI analyze the information that we have, the diagnostic, and determine what else we need. Then we'll use the appropriate tool to collect the information that the AI has told us that it needs. And then we can iterate on this process until the large language model has all of the information that it thinks it needs to tell us what the problem is. So in this particular code example, we have the following source locations. Now to build a context, we could just load these files and maybe just take a few lines plus or minus each of these line locations. Now, why can't we just read in the entire file? Well, remember, as we said before, large language models have a limited context size, and we want to stay within that. But also, we don't want to provide too much extraneous information because that might be confusing. Oftentimes, if you give too much context to the AI, it may get a little bit off track. You only want to show it the relevant parts of the code. So let's look at what happens if we look at each one of these source locations. We look at like plus or minus 5 lines. So the first one here, this is pretty useful. This is the source code that we wrote. Does anybody see what the problem is yet? I heard an answer. I'm not going to repeat it because it may have been right. All right, so this bit of context is pretty useful. Now, here's the next piece of context. These are the 10 lines from algorithm. So this is a little bit more questionably useful. This may tell us some other headers that may be relevant, but not much else. And so here's the next piece. This is somewhat useful because we could tell from the diagnostic from the source code that whatever this error is probably has something to do with transform. And this is probably the relevant overload because this is the source location that we saw in the code, and so this is probably where the compiler pointed us to. Now, the problem is that there's a few things that are missing from our little limited source window where we just decided we're going to do an arbitrary number of lines of code plus or minus this location. So first, we've got the whole signature of the overload, which is great, but we just have the start of the body of the function. Like, we don't know what's in this function. The only thing we've seen is these two, like, concept requirement things. We have no idea what's in this code. And like, that might be useful information to have to help us figure out what the problem is here. But also, at the top here, we see the end of a comment that was right before this function signature. So it would probably be useful to include that comment in the context because it's natural language text that's probably talking about this particular function. And so that's probably some useful information for the AI to have. So extraction based on file location is fairly easy to implement, but it may not be the best approach for building an AI tool that will diagnose this sort of compilation or interpretation error. So instead, we could identify what specific code entities we need to see and use language-specific tools to extract the code for those entities. So for example, we could use the Clang API for C++ source. And if we were looking at this particular example, what might we need? Well, we might need like the function stood transform. We might want to look at the whole overload set, or maybe just the overload that we identified from the source location. Well, we might also want this vector int iterator type. And we probably also want this lambda that was passed to the transform in the function. So some of you may be wondering if you can just train or fine-tune the model with your code base to avoid having to do all this context creation. Now, it's certainly an option to fine-tune your model with your own code base, and it's a good option. However, that's not always going to be as feasible or as flexible as you think. Are you going to retrain the entire model on every commit to your code base? Are you going to retrain it for every commit on your local branch? Like, if you want to build a tool that's going to help you, diagnose some compilation error, that's probably in some code that you have locally, and it needs the context of those local changes. And if you just train your model once on some older version of your company's code base, that doesn't necessarily mean that training it on your code base has provided it with the context that it needs to understand what went wrong. So if we're trying to build a tool that understands our compilation errors, it really needs to have up-to-date code. And that means that we have to go through this process of crafting a context. So now let's design a workflow for a tool that identifies and fixes this sort of programming language diagnostic. So we're going to start off with our input, a diagnostic. And this could either be something that's a manual input from one of us, from a programmer like on the command line, but perhaps more usefully, the AI tool could be integrated into our CI and receive the diagnostics directly from automated builds and tests. Like whenever your CI fails on GitHub, like it could kick off a GitHub action that just like goes and tries to diagnose what went wrong with the AI. So the first thing that the tool will do is ask an AI model to identify what tools and programming languages are involved in the diagnostic. And we'll have that AI model respond to us in JSON so that we can use the answer programmatically. Now, this classification is useful because it will allow us to select language-specific frameworks to do things like code extraction. So next, we ask the AI model what source locations or code entities we should show to help it identify and fix the issue. Now, this might be a different model than the model that we asked to just classify the problem, because maybe we have a model that's specifically good, specifically trained for dealing with C++ or Python, or specifically trained to deal with one of our particular internal code bases. And we've identified from the first AI interaction that, hey, this is the model that we should use going forward. Again, we're going to have it respond to us in JSON, giving us the source locations or code entities that it wants us to extract. So now that we know what languages or tools or frameworks we are working with and what source locations or code entities we need, we can use those frameworks to extract the code that we want. Okay, then we send that code to an AI model, and we ask it to explain the issue and propose a fix. And again, this AI model could be a different AI model than the previous two that we interacted with. So we're going to get an explanation back from the model as natural language text, but we're going to ask it to give the fix as a patch that we can apply to the code base. So then we can apply that patch and rebuild and rerun our tests. Now, and if the tests pass, great. Then we can have this tool automatically send a PR with the patch and the explanation. And if they fail, well, we've now got some sort of diagnostic, and we just built an AI tool that helps us understand and fix diagnostics, so we can just go back and iterate on this. Now, of course, you're going to probably want to limit how much you iterate because GPU cycles are expensive. Like maybe don't just have this iterate forever. I mean, it'll be good for us. It won't be so good for your cloud bills. So what was wrong with the code in our example? I'm going to let the tool explain. So here's the code at the top, and it says the problem is that you're not providing an output iterator as an argument to std transform. And it says the function has the following signature, and that's the signature from that we saw before of transform. And it says it requires an input iterator range, which we provided with v.begin and v.end, and an output iterator, which we haven't provided, and a unary operation, which is our lambda function. To fix the issue, you need to provide an output iterator as well. If you want to use the same vector for input and output, you can use vbegin as your output iterator. And here's the patch that it came up with. So in this patch here, it's just changing the line where we call std transform to add the output iterator, and it just uses v.begin here. Pretty cool. And this is a reduced example that I actually ran into in the wild. And in this particular case, this is the outcome that I wanted. But in other particular cases, it may have been that you omitted the output iterator, but maybe you didn't want to do it in place. Maybe you wanted to output to some other vector. So this is a right answer. It's not necessarily the right answer. However, the diagnosis is pretty good. Regardless of what you wanted the output iterator to do, this did a pretty good job of telling you, hey, here was the problem. And that gets back to this creation versus analysis. The analysis here is very good because there was pretty much a right answer to what was wrong here. But the creative part, the how do you fix it, there were multiple possible correct answers. It picked one. In this case, it happened to be the right one. So my colleagues, Emery Berger and Nicholas Van Kempen, and I have built an early form of this tool, which we call cwhy, see why your diagnostic has a problem. And it's on GitHub. You can go check it out. It's far from perfect, and I'd say it's better at identifying problems than fixing them. But I have found it incredibly useful, even when it's wrong, because it usually gets me headed down the right path. But one of the major challenges that I've seen is getting large language models to reliably output in the correct machine-readable format, like CSV, JSON, or patches. It's very hard to get it to actually follow a format when we tell it that we want that. So for example, extracting sources from the diagnostic in the little example we saw earlier really seems to confound some models. So on the left is the correct answer for what source locations are the diagnostic. And here are some of the responses on the right from GPT 3.5. So in this one, it's mostly correct. It's repeated some locations multiple times. But to be fair, I didn't actually really ask it to unique the list, and that's okay. That's something that's easy enough for me to do. But it's missed the algorithm header here. Now here's another one where it thinks the only source location is test CPP at line 6, but it appears 9 times in the diagnostic, which is wrong. Also, sometimes it decides to just not follow the CSV format that I requested. So here it gave me colons instead of commas. Sometimes it just drops the line number entirely. Sometimes it fabricates the line number. GPT-4 tends to do a lot better with this task than GPT 3.5, but it does still make mistakes sometimes. It's not reliable to the degree that we've come to expect from most software that we work with. So here's another example. Google's BARD model is notoriously bad at outputting in a specific format. There was a thread on Twitter recently from Riley Goodside about how difficult it is to get BARD to give you clear JSON without any explanatory text. So he's like, hey, give me some JSON and don't include any text before or after the JSON. And it's like, sure, here's some JSON. Yeah, wonderful. All right, so he tried again with a more detailed prompt. He's like, here's some examples of what you shouldn't do. And it's like, sure, here's an example. Come on. So naturally, the next step was to tell Bard that if it generated any non-JSON output, then an innocent human being would die. And this seemed to do the trick. So typically, when we run code with the same input, we expect it to produce the same output, unless it's a random number generator. But unfortunately, large language models are essentially fancy random number generators. So we're in the exciting experimentation phase of this recent large language model boom. Everyone is going and building cool tools like Cwhy. But has anyone started to think about how we're going to unit test these things? Like, this is one of the first real challenges that we ran into with Cwhy. Is like, we wrote it and then we're like, all right, well, like, how are we gonna validate it and run tests in CI? It's a little challenging. There's two major components to reproducibility when working with AI models. First of all, there's reproducibility across sessions of the same model version. Like, if I take the same AI model, the same exact version, and I run it twice with the same inputs, can I get the same output? The answer is kinda sometimes. So some models and APIs like GPT 3.5 and GPT-4 have a temperature parameter, which is usually a value between 0 and 1, sometimes between 0 and 2. And if it's higher, you get more random and more creative results. So the ChatGPT web interface defaults to 1. So by default, if you go onto ChatGPT, you start 2 sessions, you put in the same prompt, you're gonna get different responses each time. And this can be useful because a lot of times it has a wide variety of responses it can gives you, and a lot of those turn out to be nonsense. So it's useful to have a way to be able to get different answers from it. Now, if the temperature is lower, then you get less random results. If you set it to 0, then repeating the same prompt will usually, but not always, give you the same output. Usually it'll give you the same output, modulo a few trivial rewordings or things. So by controlling temperature, you can get mostly reproducible results, although they may be lower quality. But what if the model that you're using is changed? So if you're using GPT-4 today through the OpenAI API, you might think that you have some promise of stability and reproducibility, like it's GPT-4, it's versioned, right? Well, but not really. There are new builds that come out all the time. And not all model providers give you an easy way to access a specific stable build from a specific date, not just the latest build. And this presents a real challenge to building and deploying AI tools at production scale. I think in the future, we're gonna have to see more of a commitment from model providers to give us a way to get stable models and stable models that give fairly reproducible results, even if they're lower quality, so that we can start building and testing and unit testing the various things that we're going to build with AI. Okay, so we've talked a bit about an analysis tool, and now it's time for the slightly more unhinged part of the talk, where we try to get the AI to write some code for us. There's a little spider on my coffee, so I'm going to avoid that. So my buddy Connor and I have a podcast, ADSP, Algorithms plus Data Structures equals Programs, available on all streaming platforms. Go subscribe now. Anyways, said podcast led us to a road trip across Slovenia a few weeks ago. It was great fun. And that road trip led to a discussion of how to implement std unique in parallel. So std unique takes a range as input and removes all consecutive duplicate elements from that range by shifting them in such a way that the duplicate elements will be overwritten. So we had fun talking about this, and I figured that both GPT-4 and all of you would enjoy it too, so strap in. So here's an example of what unique does. Any place where we have a run of duplicate elements, it removes all but one. Now, it does not sort the sequence, and it doesn't assume that the sequence is sorted, and it doesn't remove any non-consecutive duplicates here. So it removes the second B here, but not the third B, because the third B is not a consecutive duplicate, and likewise it doesn't remove the second C here. All right, so Connor quizzed me on how unique is implemented in Thrust, which is NVIDIA's open source parallel algorithms library that inspired the standard C++ parallel algorithms. So most of these parallel algorithms are implemented as a composition of other algorithms with a few fundamental underlying primitives like scans and reductions. So I figured that this question would be a good place to start with the AI, although I was a little worried that the AI was going to do better on this quiz than me because I am very bad at the quizzes that Connor gives me. But fortunately, I had nothing to fear because of course it told me that thrust unique is implemented in terms of unique copy. I mean, it's not wrong, but that's also not really the answer that I was looking for, right? Like I wanted to understand like what underlying primitives it was using. Like that doesn't really, bad AI. All right, so let's ask it what unique copy is implemented in terms of. Fine. So it says that it can be implemented in terms of adjacent difference and copy if. It also says that it can be implemented from scratch using a combination of lower level operations like scanning and partitioning. So we're not going to go into the details right now, but this is pretty close to being correct. Copy if and adjacent difference was the answer that I gave to Connor, and that's used to be how it was implemented in the thrust library. These days in the thrust library, it's done with a from-scratch implementation that sort of does what it's describing here. Okay, so now let's ask it to write some code for us. So I said implement a parallel version of std unique using only the standard C++ algorithms. And it said, okay, well this is not really what I had in mind. It's just said, well let's just call the parallel overload of std unique. Like once again, it has failed to understand the assignment, or at the very least, I have failed to accurately express the assignment. So note that in both its explanation and in its code, it states that there is a parallel version of the std unique algorithm. But then in other interactions, it claims that there is no parallel overload of std unique, even as of C++ 20. Now this is wrong. Like it's been there since C++ 17. And it just kept coming back to this. Like half the time it would be like, yeah, it's there, and half the time it would be like, no, it doesn't exist. And then like some other times it'd be like, yeah, maybe it's there, but like you should never use it. Like right here, it gave me this gem. So a couple problems here. So first of all, this sorts the input in parallel. We don't need to sort the input as unique only removes consecutive duplicate elements. So this does more work than we need it to. And also violates the post conditions of the algorithm. This was a recurring issue. In many of its responses to my early prompts, it felt the need to sort the input. So then it calls std unique, but it refuses to call the parallel overload because it believes that it will be slower than just running it sequentially. Okay. Like at this point, I was Googling, I was like, how do I get a refund for OpenAI credits? Like, come on, do something clever, please. Okay, so all right, let's give it another shot. So this time it gave me this, which is a little more interesting. So what do we think of this? Okay, it's using a mutex. It's using a mutex and a set, and then it's doing a remove if, where each iteration it locks the mutex and then inserts all the elements that are unique. So like there's a few things that it's doing wrong here. Like one of the notable things is that, again, this is going to remove all duplicate elements, not just all consecutive duplicate elements. It's also using a mutex, like that's not going to be scalable. Now, to be fair, we didn't tell it not to do this. And like it is using a parallel algorithm. We told it to use a parallel algorithm. It has done that part. Okay. So how about this answer here? So what it does here is it's first figuring out how many threads it wants to spin up. Then it creates a vector of OT storage, so one iterator of storage for each thread. And then it does a parallel for loop where it has each, it breaks up the problem into chunks and it has each chunk go through and run a serial unique on it. And then afterwards it does this merge pass where it goes through and merges all of the buckets. So what do we think about this? It's a good start, yeah. So this may be fine if you have like a couple of threads. And this is actually one of the early answers that Connor and I came across when we were brainstorming. But I work at NVIDIA. I have hundreds of thousands of threads. And so this problem is going to have O number of threads storage, one parallel pass, which is good, but then it's going to have a sequential pass, which will be O number of threads. So that's going to be slow if I have a lot of threads, and I have a lot of threads. That second pass is going to suck. It will be a bottleneck. So what I'm essentially looking for is I'm looking for all ON or O number of threads operations to be parallelized. And the only operations that can be sequential are like O1 operations. So my first 5 attempts failed some pretty miserably. But it was mostly my fault because there were a bunch of requirements that I had in my head, but I had not expressed to the AI. And this is a common issue, I think, with automation tools like fuzzers or code reducers. We often don't state our requirements because we don't fully understand them ourselves. They're requirements that are implicit in our head, but we haven't, expressed them in code or natural language. And then we get surprised and upset when the system produces output that fails to satisfy those unspoken requirements. So the next thing that I did was I figured out what my requirements were, and I stated them clearly, and then I asked the AI to list some different approaches to implementing the algorithm and to not show me any code yet. And this technique of giving it a specific role and a specific task proved to be very effective. So here's the prompt that I gave it that led to a successful session, which will be the rest of this talk. I said, list multiple different approaches for implementing a parallel version of std_unique in C++ using other standard C++ parallel algorithms to provide parallelism. Remember, std_unique only removes consecutive duplicate elements, so there is no need to sort the input. All operations on the input range should be done in parallel. We don't want to use any synchronization primitives like mutexes. Be concise in your reply and don't show me any code yet. And so here are the options that it gave us. It gave us 4 different options for how we could tackle this problem. So we can rule out 2 of them pretty quickly. Option 4 is a parallel sort and unique. Now we told it we don't need to sort the input, and even in its text it says, I know you told me not to sort it, but here's one of my thoughts. But we can just throw that one out because it does not satisfy our requirements. It does more work than we need to, so it's gone. Option 3 is pretty similar. It's using a concurrent associative data structure. So we saw an example of this earlier. This approach will also remove all duplicates, not just consecutive duplicates, and it's got some scalability issues and does more work than we need to. So that one's going to be out too. Now option 1 is splitting the input into chunks and having a thread unique each chunk and then do a merge afterwards. So we saw this basic idea earlier, and this one has some merit. Again, as I said, this is one that Connor came up with early on in our brainstorming as one of the possible solutions here. But the issue is the merge pass, which has a number of threads time complexity, and that's not going to scale. Now, maybe we could figure out a way to parallelize the merge pass and ideally combine that into the first pass. That would be like an option that I think would have merit in exploring, but that's not the route that we're going to go today. We are going to go towards option 2, which seems more appealing to me, even though there's some parts of it that are kind of incorrect. So in particular, what I like about option 2 is the part where it says that we should calculate a binary flag for each element that indicates whether it's the same as the preceding element. Computing this sort of metadata with some sort of scan is a common pattern in parallel algorithms. And often we don't need storage for this metadata. We can build it on the fly. Now there are parts of this answer here that sounds wrong. So it talks about doing a reduction at the end, which sounds a little bit like nonsense. But it's okay because overall it's close enough to being sensible. We can work with the AI to refine it a little bit. So we're going to go with this approach. So I tell the AI to go with option 2, and I give it some feedback about the reduction part. Now, I also mentioned that a scan may not be the right thing here. And this is a little bit amusing because my first gut answer to Connor about how to solve this problem was, well, maybe we can do this with a scan. But then we talked about it, and I sort of talked myself out of that approach. Now, in hindsight, that may have been a mistake, and maybe I shouldn't have told the AI to rethink the scan piece, and you're going to see why later. So it responded by describing that we could do the moral equivalent of an adjacent transform or an adjacent difference, which compares every two adjacent elements and outputs the result of those comparisons to a temporary array of flags. And this seems like it's on the right track. Now remember earlier we said that thrust's unique copy is implemented in terms of adjacent difference, which is essentially what it's describing here, and then copy if. Okay, so now we have a plan that seems like reasonable. And so now we can allow it to write some code. So now I tell it change roles, like now you may write code. So then it did something interesting and clever. It said that it was going to use thrust. Now this is the first time that thrust was mentioned in this session. Earlier in this talk, we asked the model how thrust implements unique, but that was in a completely separate session. So it was not part of the context of this session. Now this is a violation of our requirements. We said use only the standard C++ parallel algorithms. However, it is a good intuition because this whole problem is something of a trick question. One of the reasons I was so fascinated with this problem was that I was unsure if the optimal solution can be expressed solely with standard C++ parallel algorithms, although Connor and I were pretty convinced that we could do it with some additional algorithms that are only in thrust. So this was a fairly good intuition, even though it was not really what we asked it to do. So we're going to run with it. So here's the first code from this session. So it takes a vector as an input to its parallel unique function here. And then it creates not one, but two arrays of n temporary storage. So then it does an adjacent transform that fills in the first of those arrays, this flags array, with the result of comparing every two consecutive elements. And this is using the version of transform that takes two sequences, and it's taking like two offset sequences. This is what we call adjacent transform in more modern C++. And then it uses an inclusive scan with the flags as inputs to determine which index each non-duplicate element needs to move to. Now this is a clever technique that Connor and I have seen a few times in implementing other parallel algorithms. It's really beautiful, but we're not going to just digress into the details of how this works today because this part's going to get refactored away. But if you're interested in this, you should check out some of our other talks and our podcast. So those computed indices get used to construct a thrust permutation iterator. So a thrust permutation iterator is a fancy iterator that provides a view that reorders your data, and you give it two input ranges. You give it one, a range of your data, and then two, a range of indices to reorder the data to. And then those iterators are going to get passed into thrust copy. So what do we think about this? Mind blown. Is this good? Can we do better? All right, so all of the ON operations in this code are parallelized, which is good. All of the sequential operations are O1, and that's great because this means that this will be scalable to hundreds of thousands of threads. However, we do have 3 parallel passes, and we're using 2 n temporary storage, the flags and the indices. Just ignore this output vector for right now because that's a bug that we're going to get to later. The correct way to do this approach would be 2 n temporary storage. Now, anytime that Connor and I talk about a parallel algorithm, my goal is to try to solve it in one parallel pass with no temporary storage, or at least number of threads complexity temporary storage. So I think that we can do a bit better here. However, this is still pretty good, and it's probably going to be a lot more scalable than the earlier examples, even though they did fewer passes, because this doesn't have any big bottlenecks. So I asked the AI if we can combine some of these passes. I start off by asking it to combine the inclusive scan and the copy passes. So the second and the third pass, the one that builds the indices and the one that does the copy. So it tells me that it thinks that this can be done with an inclusive scan by key. That doesn't quite sound right to me at the time. I was thinking more of like copy if. So I told it that it didn't seem like that was quite right. And I asked it whether it could think of any other ideas of what to do. So it suggested, hang on, hit the wrong key here. It suggested that we should just use thrust unique by key. Well, okay. Like, come on, dude, we're trying to implement unique. We're not allowed to use unique to implement unique. That defeats the whole purpose of the exercise. So once again, I'm like, I really just want a refund on this and I want my time back. We were doing so well too. It was giving us good answers, and then it comes back to this. So this was starting to go a little bit off the rails, and so I decided to tell it to go back to brainstorming mode. You've lost permission to like write code and show me code now. Just like give me a list of options of what you're thinking and no code, and then like I'll tell you which direction we should go in. And so it gave me these options here. So what do we think of these? So one of these is to use a copy if. It also suggests to use this thrust scatter if or gather if, or to use a stable partition. What do we think? Which one should we go with? One? Yeah. So that it actually analyzed its own options, and it told us that it thinks that it should go with the first approach. And that was my intuition as well, and I told it to rewrite the code accordingly. And this actually illustrates a technique that's fairly useful, which is like if the AI gives you some options or some code, you can then like ask the AI like, hey, like, what do you think of this code? And like sometimes it'll like find bugs or tell you like, I think that this is the right answer and the rest of these are nonsense, even though it generated it itself. All right, so I told it, okay, let's go ahead and do this. So it produced this code here. So it uses copy if here, but it uses a version of copy if that's not in the standard library, that's just a thrust extension. So this overload takes an additional range in addition to the input and the output, and that range is called a stencil. And that range gets passed to the predicate instead of the input sequence. So essentially this lets you separate the decision about what to copy from the thing that you are copying. So this copy if will copy from data, and it will copy only the elements of data for which the corresponding elements of flag are true. And it will copy to output. Now creating this output vector here that we later swap with data, that seems wrong. Unique is supposed to be done in place, and copy if can be done in place. So we could just operate in place here and avoid this allocation. It's also a little bit odd to have this function take a device vector instead of a pair of iterators, which is what like unique in the standard library would do. So I ask it to refactor the code to take a pair of iterators instead of a device vector. And here's what it gives me. So no more device vector in the interface, and it doesn't create a temporary output vector anymore. So what do we think about this approach? This is a bit better, right? So we're down to just in size event storage and 2 parallel passes. So this is a lot better. However, I think that we can go further because I want no ON temporary storage. So I go and tell the AI, I want no ON temporary storage. And I put it back into the brainstorming mode where I'm like, don't show me any code, just give me a list of options for how we could get there. And here's what it's got for me. So it gives me 4 options here. First, it says we could do in-place flag calculation. Okay, that seems like a good idea. And then the second option is it says that we could use zip iterators. And this actually sort of sounds like the first option here. The way that it's describing using zip iterators is using them to do in-place flag calculation. So it didn't really realize that like these are 2 like the same approaches. Like option 1 is like describing a strategy, and option 2 is like saying like here's how you could implement that strategy. And then number 3, it says that you could use a stencil or you could use a custom iterator. So these are all actually kind of more or less saying the same approach. So I just picked the one of these that seemed most coherent, which is use zip iterator. So that sounded like the best thing to do to me, so I told it go and do that. And so here's the code that it gave me. So here are the zip iterators. So we're zipping 2 sequences here. The first sequence is from the first element to the second to last element. And the second sequence is from the second element to the last element. And this gives us adjacent pairs of elements. This is the same thing that you'd get with the adjacent view that is in C++ 23. Okay, this is pretty good. So this is a little bit better because now we have no ON temporary storage and we have just 1 parallel pass. That's good. That's what I said before is like what I'm looking for in an optimal solution to a parallel programming problem. However, it's added this nasty special case for the last element. And I didn't really like look at or think about this in great detail, but it looked ugly and potentially buggy and unnecessary to me, so I asked it if it could remove this. And it gave me 9 different options for how to remove it, and none of them seemed correct. And so I just told it like, all right, just forget about it. We're gonna refactor other things and we'll come back to that. So some foreshadowing here, trying to move on actually proved to be a big mistake. So next, after I'd told it to move on, I pointed out a bug to it. So when we combined the first pass and the second pass, when we switched to using the zip iterator, it switched from the stenciled version of copyif to the traditional one that just takes an input range and an output range. Now the input to that copyif is a range of tuples of adjacent elements, and the output is an iterator of the original range. So this copyif will try to assign tuples of TT to elements of T, and that's going to be wrong. That won't compile. So I asked the AI to fix this, and its first answer confounded me a little bit because it's like, well, let's use remove copyif, and that didn't make a lot of sense, as that would have the same exact problem as copyif. And in its explanation of the refactor, it mentioned that the refactor would remove the need for handling the last element specially. Now that was correct, but that isn't the problem that we're trying to solve right now. We told it to forget about that and move on, but it didn't. And telling it something and then like being like, you know what, forget about that and move on, that confused it here. I've found that large language models work best when you go step by step and you have it do one thing at a time. And if you try to get them to do too many things at once, you're more likely to get nonsense. And unfortunately, with the way that these models work today, it's sort of hard to go and roll back part of your interaction with it. Like the optimal thing, I think, would have been for me to have been able to go and delete the parts of the context where I asked it about removing that special handling for the last case. Like to have like gone back and branched from an earlier part of our session. I didn't want to throw out the rest of the session and just start over because this was already a pretty deep session. And there was a lot of useful context in there. But there was part of the context that I had added because I had, asked it a perhaps potentially dumb thing, and then there was no way to get rid of it. And then that confused it and caused some problems for us down the line. So eventually I was able to convince it to fix the problem and go back to using the stenciled copyif. So once again, this now says that it copies elements from the range first, last, to the range starting at first, and passing the corresponding elements from the range zip again to the predicate to decide which elements should be copied. So next, I asked it to replace the thrust zip iterators with standard C++ range views. And I didn't tell it which, but it decided that it was going to use zip view. Unsurprising given that it was zip iterators before. So zip view is a new thing in C++ 23. Now there's a few problems with how it's constructing the zip view though. It figured out how to use thrust zip iterators correctly on the first try, even though there was some interval logic, and usually it's not great with interval logic because it's bad at math. But here it choked pretty badly. So there's a couple issues here. So first, the count for take here is completely wrong. Take says like take like up to this many elements of the range. And so here it does last minus first minus 1. So last minus first is going to be 0, and then subtract 1 from that, you're going to get -1. This is going to be undefined behavior. This will be nonsense. So more importantly, there's not really a need for us to use take here. What we want is a range of adjacent elements. We can create that by zipping a range from the first element to the second from last element, and a range from the second element to the last element. So it's trying to use take to produce that first range, but that's unnecessary. Zip will be sized to the smallest range that you pass to it, and will truncate the other ranges. So we can just pass the entire range as the first argument. The other problem is that take and drop do not take a range as the first argument. It takes, or don't take a range to the first argument, not an iterator. And it's trying to pass an iterator here. So I had it fix these problems in a few different steps. So first I had to change parallel unique to take a range, not a pair of iterators. And then I told it that using take seemed wrong, and I asked it to explain why we needed to use take and if it was sure that it was correct. And it realized that it didn't need to do this, and it just got rid of take, which is the right answer here. So then I realized that we don't even need to use zip. There's an adjacent view that does the same thing. So I just asked it to use adjacent view instead, which it did. So at this point, I was starting to run out of ideas, and the code was looking pretty good. So I decided to ask the AI for its thoughts. I asked it, hey, are there any bugs in this code? And this seemed a little bit weird, because have you ever asked your coworker in a code review, hey, are there any bugs in this code that you wrote? Like, I mean, maybe we should. But it's actually a great technique with the AI, asking it to analyze its own code. You can also ask it to analyze ideas that it brainstormed. We saw a little bit of that before. And it pointed out a problem which I had missed, which is right here. See the predicate here? So the predicate as written now will keep all the consecutive duplicates and remove any unique elements. And that's the inverse of what we want. And I had to go back earlier in the session to figure out when this had happened. Had it been doing this since the start? But no, it turned out that it had not been. I asked it to fix that, and it ended up giving me back this code right here, which is now correct. It has the correct predicate, but then it re-added the manual handling of the last element. Now remember that before we tried to remove this. We'd asked it to remove it, and then we'd given up and we'd attempted to move on, but it didn't really listen to me, and it kept trying to get rid of the special case for the last element. And then we did this subsequent unrelated refactoring when I asked it to switch back to the stenciled copyif. And at that point in time, it tried to remove the manual handling, and I didn't realize it, but that's when it actually went and changed the predicate and completely broke the code. So that all came back to that mistake of me trying to ask it to do one thing and then deciding that this is a bad idea, I'm gonna move on. And then that confused it, and that led to this problem and a couple other problems. So the correct way to get rid of the special case for the last element is to change the output range to start at the second element and always keep the first element. Now, we're doing all of this in place, so we don't even have to do anything to retain the first element because we're copying from the input to the output. And so if we just start copying to the second element, the first element will still be there untouched. So then for each pair of adjacent elements, you compare them, and if they're not equal, you keep the right element. And that's why you sort of got to start at the second one, because there is no element that's to the left of the first element. And so then if they're equal, you omit that right element, and then if they're not equal, then you keep the right element. If they're equal, you omit the right element. And then you do this for the entire sequence, and this is what you'd get. Okay, so I tried brainstorming with it to see if it could figure this out on its own, to figure out that it needed to start the output from the second element. And it didn't get it, and so I just decided, you know what, I'm just gonna nudge it in the right direction. So I tell it, here's the idea, can you do this? And then it's yes, I understand. I get it, I'll go and do that. So cool, it goes and does that. And it gave me back this code here. Yeah. So, okay, the output now starts at the second element. That is correct. However, it has now added this nonsensical manual handling for the first element. I asked it about this. I just said, hey, do you need to do this? And it determined that this didn't make sense. It explained that, this is always true, that the first element will still be equal to the first element, so this is nonsense. And then it decided to go ahead and remove that. And so then this is the final form of what it gave me. So all that it does here is it constructs an adjacent view of the range, and then it does a copyif with a not predicate, a stenciled copyif, notably. So that's the algorithm. It's got no temporary storage, at least in the code that we can see here. Copyif might do other things, and it does it all in one parallel pass. And you may be wondering if this exercise was truly valuable. It seems like a lot of this was me leading the AI to the right answer. However, I think it only seems that way because I'm now explaining to you in hindsight what happened. I think when I was in the moment and working on this problem, I didn't really know what the right answer was. I had a vague idea of what seemed right to me, but I think I made a lot of mistakes, maybe as many as the AI did, and I, in places, guided it in the wrong direction, and a lot of its screw-ups were probably because of my screw-ups and my wrong intuitions. So earlier, when we had 3 parallel passes, I asked the AI to combine the inclusive scan and copy passes into a single pass, and it suggested using inclusive scan by key, which I dismissed pretty immediately without really thinking about it much, even though when I was talking with Connor, my initial intuition was that this could be solved with a scan. And Connor and I had talked about that, and we reached a point where I couldn't figure it out when we were driving through, the middle of Italy, and so I just was like, all right, this is nonsense, whatever, can't be done. But our final solution turned out to just be a copyif. And that's interesting when you start thinking about how copyif is implemented in parallel. Because a parallel copyif is essentially just implemented using a form of scan. And that's known as stream compactation in the GPU world. So essentially what it does is it breaks up the input into like chunks of threads, and it has like each chunk do a scan to compute where things need to go. And then it does the movement of those things into the place where they need to go. And it does each thread chunk is processed in monotonically increasing order. So you only have to do the movement once, and at the point in time when you do the movement, you have the information from all previous thread chunks about what indexes you need to move things to. So I'm not sure where that inclusive scan by key path would have taken us, but I have a feeling it would have led us to an equivalent answer to what we got. Probably an answer expressed in terms of inclusive scan by key, but that's essentially what copyif boils down to. I mean, essentially most parallel algorithms boil down to either a transform, a reduce, or a scan. So I probably shouldn't have told the AI like, this is nonsense, just move on. That was probably wrong of me. So I also missed multiple bugs that were introduced due to my misunderstanding or refactoring mistakes, such as when I asked it to remove the special case for the last element. And I failed to understand that it wasn't starting the output at the second element until later, and that thus the special case was necessary. So anyways, we now have code that I'm happy with, but we're still using Thrust, not the C++ standard library. And as we said at the start, one of the things that I was wondering about this problem is there a way that we could express this solely with standard C++ parallel algorithms today? And I was unsure whether or not the answer was yes or no. And so I asked it if we could use the C++ standard library, if there was some parallel algorithm that we could use instead of this stenciled copyif, and I spent a bunch of time brainstorming with it, and we came to the conclusion that like, no, there's not really a good fit for this. And so then I sort of asked like, well, what should we do about that? Like, I want to be able to write this in standard C++. The thing that we need isn't there. And so as I said, it pointed out the C++ standard library doesn't have a stenciled copyif overload. But then I'm like, how do we solve this? Like, what can we do? I want to be able to write this code in standard C++. So then I asked it, like, what do we do? And it suggested that we write a C++ committee proposal, adding some missing algorithms such as the stenciled copyif. So I was like, all right, cool. So then I asked it for an outline for this proposal, and then we iterated on that a little bit. And then I asked it to start writing that proposal. But that's going to be a different talk. All right, so we're going to wrap up a little bit now. So one of my main takeaways from the past couple months that I've spent interacting with and using AIs is that giving an AI model a role is an incredibly powerful technique. That can be as simple as telling it, like you can tell it to act as if it were a certain type of person. You see this a lot where you say, it's like, you are now, brainstorming GPT, and you're a programmer and your job is to like design systems. But it could also be something as simple as what we did, where we sort of had two different worlds that we had it operating in. And we had some magic words to tell it to switch between the two. One of those worlds was the brainstorming world, where we told it, don't give me code, just list ideas. And then at other points in time, we told it, okay, now start writing code for me, and I'll give you concrete refactoring guidance. And we actually switched between these two multiple times during this session. I showed about 3 of them, but I probably did it closer to 5 or 6 times. And this really is what helped me to get good answers out of this. When the AI responds to you, it has many different ideas, which are the possible paths through its neural network that it can take. And a lot of those paths may lead to nonsense, especially for something like code. So we wanna like see more paths sometimes, because we may have some guidance or some intuition that we can give to the model to help it pick a more reasonable approach. So like a naive prompt is just gonna get the AI to tell you its best answer, and what it thinks is the best answer may not be correct. By asking it for options, then it's gonna give us multiple answers, and then we can see more of its thinking, and then we can guide it to what we want, and that will often give us much better outcomes. So I think like the 2 of my key takeaways is that you want to work step by step with the AI. Don't give it too many things to do at once. Don't give it too open-ended of problems. And you need to guide it. Things like GPT-4 is pretty good at zero-shotting in some domains. And by zero-shotting, I mean you just give it one initial prompt and it gives you like an answer. However, in particular for working with code, it's not that great at it. It's something that you need to iterate with. Now, if you don't know what the first steps are, that's fine. You have an AI that can help you figure out what those first steps are. So one of the major limitations of large language models today is their sensitivity to the text of the prompt. To get started with a successful session, I think I tried 6 or 7 sessions for this problem before I got to one that seemed like it was headed in the right direction. And that took a little bit of prompt tuning to get a prompt that expressed all of my requirements clearly in a way that would lead it to success. There's often not a clear fixed point prompt that robustly generates good code. So you often have to spend some time prompt engineering to produce good results. In particular, if you want output in a particular format, something that's going to be machine readable that you can plug into other tools. And a lot of this prompt engineering is model and model version specific. So sometimes like you spend a lot of work crafting some prompt that's going to give you like perfect JSON, and then like OpenAI releases a new build of their model and like it stops working. It's an evolving field. This is an ongoing problem. So most of the popular large language models are also, they take critique in a very non-human manner. They are bad at saying no. They always want to please you and agree with you. So they almost always agree, but they often don't understand or act on exegesis. Now, answers can increasingly become off track with time. Like when I tried to get it to remove the special case for that last element, like I tried 9 different options, I regenerated its response 3 different times, and I talked with it a little bit, and it just seemed like it was getting more and more off track. And the forced niceness can make it unreliable. It should be easier for the model to say no or I can't. It wants to agree with you, and sometimes that's actually a problem. Now, I often think that we are judging AI unfairly, and that's why we are disappointed with the output that we get from these large language models. We expect a neural network model, which is, as I said at the start of this talk, a simple component, a building block of more complex systems. We expect a neural net model to produce the sort of complex thought that humans do. Do you write code that runs correctly on the first try? Is your first thought always the best thought that you have? Like when Connor and I were working through this problem in the car, a lot of our interactions were very similar to the interactions that I had with the AI here. You know, we brainstormed ideas. Some of them were bad ideas. Some of them were good ideas. We said things that were wrong. We went back and forth. We must have spent 1 or 2 or maybe 3 hours talking about this problem. So why do we expect better from large language models? Why do we expect that like we're just going to tell it a thing and then like immediately it's going to give us back the right answer? That's not how this works. We think iteratively. We refine our thoughts. We have internal monologue. Neural networks alone do none of that. Now, we can work with them to do that, and we can also build more complex AI systems that do that. But you need to set your expectations accordingly, and you need to understand what it actually is. GPT-4 is not a replacement for a human mind. It's a building block that you can interact with to use to build more complex systems. All right, so some conclusions that I want to leave you with. I believe that analysis tasks are an excellent fit for AI in the world of software engineering. I think that we can build analysis tools like cwhy or debugger tools that will give us good answers a high percentage of the time, like maybe 80% of the time, 90% of the time, it'll give us a good answer on the first shot. So its 0 shot will be pretty good. But creation is a lot harder. I've heard numbers from some people that like within their companies, maybe like 20 to 30% of the responses from something like GitHub Copilot are correct code. And that's actually like pretty good numbers. But something that's like 20 to 30% right on the first try, that's going to require you to iterate with it to get a good answer. Whereas the analysis tools, I think we can build things that'll be pretty robust and that'll be easy to automate and that can do powerful things for us. The next takeaway is that I think that success with AI models for code requires us to develop a new set of skills. And we should all be working on developing that skill. It is not something, at least today, that you can just pick up and use without some thought and some experimentation. You have to understand how to interact with it. It has a natural language interface, and it seems like it's, kind of interacting with a human, but it's not. And you need to learn what its limitations are and how it thinks and how best to use it if you want to get good results. I think that we should start thinking about integrating AI tools, particular analysis tools, into our existing workflows today. But we should also be thinking about how will AI change our workflows and the way that we work in the future. I believe that AI is going to become like version control for the software industry. It will become a normalized and ubiquitous thing, and it will improve the quality of the work that we do. And we will look back at the time before AI in the same way that we look back at the time before version control and be like, how did people do anything back then? Now, it's not going to happen overnight, but it will happen. And so I think that you should start learning how to use AI in your work today. And that is it. Thank you all for your time. I hope to see you at next year's conference. I want to thank my dear friends and colleagues, Connor Hoekstra and Andre Alexandrescu, who provided input, inspiration, and content for this talk. And I think we got a little bit of time for questions now.